thank you, Carol, for the opportunity to talk about it, even though this is really your topic. But I love the term core values, because the core is to recap kind of what Bill talked about last week. It's where it all comes together, and it actually has to be a Swiss watch because of the issues of constructability. It has to be as tight as possible because of the immense cost of building these buildings. So every square foot that is in the core is a square foot taken out of revenue generating space. So we very much focus on, as a matter of fact, I think I was telling Carol before we started, we probably spend more time designing the core, and I'm using the term designing kind of loosely because a lot of it is kind of negotiating, because just about every mechanical, electrical, plumbing, fire, life safety, architectural, structural thing happens in the core or goes through the core. Without the core, you can't get up the building. So we're going to talk about core value, architectural technical design in the heart of the Supertall. And to recap again what Bill said, there's a structural core and there's an architectural core. And in the best of all worlds, in super tall buildings, they are kind of one and the same. It's kind of a twofer, as I would call it, as opposed to a freebie, because it is quite a challenging thing to design the core of a building. So I always, since it is architectural, I always fall back on the 3 Vitruvian principles, which is firmness, commodity, and delight, just to test that it is architecture. And I think without a doubt, it's firm. It provides the core strength to the building, and especially in the typology that we're talking about, the 21st century Supertall, which is generally a core building with mega columns and outriggers. And it also has to do with the serviceability of the building. So these are some diagrams of what are called the modes of translation. And you'll notice the building, because of wind, because of seismic, will deflect, will move. You know, remember, again, going back to Bill's lecture, this is a cantilever. It's a beam stuck in the ground, so it's gonna move with lateral forces played on it. But also, don't forget, there's also a torsional component. So it's not just moving side to side. It actually, especially in a building with wings like this one shown here, it's gonna twist. And all those movements need to be controlled. Firmness, check that off. Commodity, which can be another way of calling functionality, is I'll call it the architectural reason for the core. There's all sorts of stuff that we stuff in it, and we'll go into a little more detail with that. But the functionality of the Supertall would not be, a Supertall wouldn't be functional without the elevators, wouldn't be functional without the exit stairs, and it wouldn't be functional without the fan rooms and MEP closets and risers. And then, of course, last but not least is delight. And I will argue that there is beauty in the core. And actually, I find this image just wonderful. I've got a black and white version of the one that Carol had in color. But I find it thrilling to look at a building under construction. But it's also can be a surprise and beauty. This is actually what the inside of that core in the previous picture looks like today. It's the atrium of the Grand Hyatt in Shanghai in the Jinmao building. So it has all the 3 Vitruvian principles. So it is architecture. So now we're going to talk about what Carol really wants me to talk about, which is the primacy of the center core. And in all of the buildings that Carol characterizes as supertalls, anything over 380, the core is in the center of the building. And not that there aren't some outliers or other ways of doing it. And these are some examples of some offset cores of some very tall buildings. maybe not 380 meters, but several of them are over 300 meters. And you might put the core, you might offset the core for reasons of climate, maybe for site constraints, for reasons of view, or programmatic reasons to separate the elevators so you have two distinct entries for two distinct functions. But we're not going to talk about that. What we're going to talk about is, as Carol would like to say, the new typology, the 21st century typology, which arguably was first expressed in Jinmao, which Mark Sarkeesian is going to talk in depth about in a couple of weeks. And you can see those elements that we talked about. Here's the concrete core, center core. Here are the mega columns. You don't see the outriggers, but the outriggers, you can see the lines that the outriggers fall on. And then at the top of the building, the core still remains, the structural core still remains, but the architectural core has shifted. The architectural core, the exit stairs are now outside here. The firefighting elevators are outside here. The passenger elevators have shifted to an element within the core. And here's the second firefighting stair. And then all the mechanical shafts are now distributed, because this is a hotel, outside. So what you're left with in the hotel atrium is this very soaring, very wonderful space. So why is the core in the center? Well, I think it has to do with optimization and what I call serendipity. It's the optimal structural location. It's the optimal location for occupant circulation, as well as services distribution. It's also the optimal location to have a consistent perimeter lease span. And that is, as you remember from Bill's lecture, that is the space between the core and the exterior wall. And as you know, I mentioned they're for buildings with offset cores. Maybe there's a reason for view, but once you're this tall, generally the view is going to be good in all directions. And every building use has kind of an optimal lease span. And so putting the core in the center will give you that optimal lease span around all four sides. Also, the constructability of using reinforced concrete is a very important thing. And where the serendipity comes in, the robustness of reinforced concrete allows us to protect all those important services within the core. The exit stairs, for instance, and the firefighting water risers, et cetera. That they're all within this very protective shell that is, gives a much more secure outlook. So I'm going to talk a little bit about the program element, the architectural program elements that are typically within a center core building in the super tall category. A typical mixed-use super tall, I'm going to use the Chengdu Greenland Tower, and as Carol mentioned, Dennis Poon is going to dedicate his talk to covering Chengdu. It's a real typical super tall, mixed use. It has four primary uses. It has office, which is about 120,000 square meters up to about this point, 120,000 square meters of floor space. Residential, which is about 50,000 square meters up to about this point. And then at the top is a hotel, which is then topped off by a kind of a super club kind of observation assembly space. It's 101 stories to this top observation assembly, and it's 468 meters tall. And as you can see, it's about 222,000 square meters. In the core, the elements within the core shared by all super tall buildings are occupant elevators, and of course their associated lobbies, service and firefighting elevators and lobbies, exit stairs, landings, vestibules, smoke control pressurization and exhaust duct risers, and MEP service rooms and risers. So here's the Chengdu core. This is at the bottom of the building. So you see all those shared elements, but in the Chengdu at the bottom three tiers are office use. So there are some unique elements to serve the offices. Those include toilet rooms for men and women. And again, if my cursor will work here, you can see the toilet rooms that generally take up, this is part of the Swiss watch thing, because we try to insert things in spaces that that have to be left void for reasons such as the elevator lobbies. We have on-floor plant rooms and/or central plant supply and return duct risers. So in this case, we have one fan room here because the floor plate is a little under 25,000 square meters. We have supplemental or satellite MEP service rooms and risers. So you can see some of the electrical rooms. You can see some of the risers in blue. There's telecoms rooms. There's other service rooms. And sometimes we have soft spots. I see I misspelled that. I made soft spots. Apologies. Soft spots for future service risers or vertical connections. These elements are not just randomly placed. When we'll talk about vertical transportation in a little more depth later on. But the elevators kind of do a dance up these supertalls because generally, because it takes so many elevators to actually serve the building, we start to introduce things like sky lobbies and shuttles serving those sky lobbies in order to get the requisite amount of vertical transportation service up the building. We'll talk about that coming on. So this is the office core, pretty typical. This is now the next tier is the residential core. Now the residential core, you'll notice it starts to clear out. So what's happened is all of the office elevators have dropped off, and what's left is the structural core and some leftover space. The trash, certain elements that residential tenants need, like trash and recycling chutes and tenant storage, start to take some of that excess space in the core. So you can see tenant storage here. There's actually a fan room on this floor because it had a central system. There's different, the electrical requirements, et cetera, are a little different. So the rooms have gone by, and then up to the next tier, we have the hospitality or the hotel zone. Now, what's happened here? The core, you notice the core walls have gotten smaller. They've gotten a lot thinner because we're higher up in the building, and we've actually shrunk the core down. What's happened, and there's two things have happened. One, the walls have actually come in on the perimeter of the core, but also the actual architectural core now has shrunk down to a minimal size. What's left are hotel local elevators, a telecom and electrical room to serve the hotel floors, and we've added a housekeeping area now. This is, for the linens and room service, et cetera. Still have a couple of exit stairs. We still have some vestibules to those stairs, and we still have a couple of elevators that are special shuttle elevators that then go up to serve the top of the tower, the observation and assembly use, which is basically a sky club in the case of Chengdu Greenland Tower. You can see we still have the service elevators, which include the firefighting elevators, a couple of telephone electrical rooms, and of course the exit stairs. But you can see how the core has now become a much smaller element, in concert with the fact that the massing of the building has tapered, so that the lease span has actually changed as well as the overall width. So what are the determining factors in this kind of design and transformation of the core? It starts with the shape of the tower floor plate and the massing of the building. Then the next element you need to think about is the mixed use, the functional group stacking of the building. The vertical transportation then is tied to the functional group stacking, and then everything that we do in the core goes back to fire and life safety, means of escape and firefighting access. So talking a little bit about the shape of the tower footprint, here are some. You probably saw some of these in Adrian's presentation a few weeks ago. The shape of the core, when you start out designing a core, you start with thinking about how it fits within that building footprint. And it sounds trite to say, but it is very important because, again, this lease span is really what they're selling. The client, the core is kind of a necessary evil to the client because he doesn't make much money on the core, but he makes their money on what's around the core. So some examples, and of course we're going to talk about Jeddah Tower at the very end. So mixed use functional stacking, again, this is our prototypical super tall, mixed use super tall, Chengdu again. The vertical transportation diagram of Chengdu is very important because this is where that, what I call the dance of the elevators occurred. In the case of Chengdu, well, in case of any building, office use, because it's primarily, it's very densely occupied. It also was occupied at the same time, generally, 9 to 5, more or less. So there are a lot more elevators to serve an office use than there are to serve a residential use, which is less densely occupied, or even a hotel use, which can be even less densely occupied than residential. So the way that it's very usual, therefore, then to put the office at the bottom of these super talls, because those elevators can be served. In this case, you'll see we have a sky lobby. We have 2 zones, or actually we have 6 zones of elevators to serve the office, with a sky lobby roughly in the middle. We then have a second sky lobby that serves the residential. And so when we talk about sky lobbies, there's a high-speed group of shuttle elevators that goes to the sky lobby where the occupants transfer, and then they go into their local elevators that serve their particular floor. And then we have a third sky lobby that serves the hotel portion, and there you transfer either out into the to get to your guest room, or to this special shuttle that goes up into the club area and observatory at the top. So here's how you can see in one view how the core changes as the elevators drop off, and you can see how the occupants will transfer from, for instance, at a sky lobby, from an office express elevator into an office local, in this case for zone 4. But then there are several zones of locals, and there are actually 3 zones of locals, as I said, in the office portion. And then as we get up into the residential, you can see the residential locals transfer from the residential shuttles, and then here the hotel locals, which you transfer into from the hotel shuttle. So hotel shuttle transfer, residential shuttle transfer, and then of course we talked about the office, and then at the very top, the vestibule core. Don't need much structure up there, so it's minimized as much as possible. Then there's another thing that design, when we talk about transformations to the core, there's also a linkage between the structural core and its mega columns and the outrigger and belt trusses. So this is again Chengdu, so you can see the structural core and see how it steps back as the building tapers. Here are the mega columns. There's 8 of them, and then here are the outriggers. If you can see these green trusses, these are, as Bill explained, these bring the forces, the lateral forces back into the core, back into that axle of the tower, and they're generally multi-stories high, and because they generally tend to be pretty large and kind of obtrusive, they break up the floor plate. We work very, very closely with structural engineers and the mechanical engineers, MEP engineers, to try to co-locate the outrigger trusses with the technical MEP services floors, which are also co-located to basically serve the different functional zones of the building. So here we have the 2 office functional zones served by, there's actually another set of mechanicals down here, served by mechanicals, by a mechanical technical floor in the middle. There's a mechanical technical floor at the top of the two tiers of offices that also serves downward, but then serves upward to serve the residential portion. And then at this juncture between the residential and the hotel, we then have the other set of outrigger trusses, the other set of technical floors that basically serve the hotel, and then capped at the top here with one last set of outrigger trusses, which then has mechanical. It serves the special function at the top and also serves the hotel. So again, this is another, I call it serendipity or twofer or whatever you want to do, utilizing that space that's necessary for the structure also as space for the mechanical services of the building. Then last but not least, just quickly, the fact that these mixed-use buildings, there can be literally tens of thousands of occupants in these buildings. And so the fact that we tuck the means of escape stairs within this concrete shell, we also have most codes now require, and this is a project in China, and China's code requires areas of refuge, which are actually sometimes sanitary, clean floors to allow occupants to come down the stairs and get out of the stairs to in a safe position before they either continue all the way down, or in the case of the current crop of supertalls, we actually tie in what we call lifeboat elevators, and I'll talk about that further into the talk. So one thing, Carol wanted to make sure that I talked about constructability of the core, and here's another construction photo of Jinmao. And Bill, I don't know what the term Bill used, but I'm going to use the term climbing factory, because in essence, the formwork and all the associated structural stuff extrudes in a way the core up the building. So this is 1995, or of Jinmao, and it was actually relatively conventional formwork. It was kind of made out of 2x4s and plywood. But in 2005, when we were doing Burj Khalifa, we developed. I'm sorry, that's my phone here. We developed this climbing formwork. Well, we didn't. The contractor did, which was Samsung, which Ahmed will talk about quite a bit, into a little more of a sophisticated assembly. It now consisted of, it actually, here's some of the gubbins that makes it climb, and here's the initial formwork that happened, but it ended up actually being about 3 stories tall, where at the very top, the rebar was being put into the void. In the middle, the concrete was curing, and below it, they could start doing things like putting inserts in for things like the elevators, the elevator guardrails. And so now this is a shot of Chengdu, and I love this shot because I'll see if I can let's see if I can zoom in. I just learned how to do this. So the formwork now, the climbing factory now consists of the 3 stories that we talked about. Here's the 3 stories inside this kind of climate protective enclosure. They're placing rebar, they're curing the concrete, and then at the bottom, they're fixing the elevator rails. But on the top, this is brilliant. They've taken the tower cranes and then have this assembly on like this turntable. So there you can see the 3 tower cranes, and I think this is an outhouse or something up there. But you can see the 3 tower cranes on this pivoting assembly, so that they can bring things, hoist things up to the position. And then now we're in 2021, and now this is another of our projects. This is called Uptown Dubai. And although you don't see it, it doesn't really show it. It's not as cool as the Chengdu shot, but inside the core now, Schindler's introduced a robotic installation system So they're actually installing the elevator rails and the other bits and pieces in there using robots. And there's a great video. You should go see this video online that shows how they actually do that. So I want before we get into a little more detail on especially before we get into Jeddah Tower, I did want to show that there are some other variations on a theme. So this is a project I think Adrian showed a couple weeks ago, where we call it Dancing Dragons, where the core is actually a series of cruciform bearing walls, basically. And you can see, it being a residential building, there's very little stuff in the architectural core, and the architectural core is kind of scattered about. Here's the one set of exit stairs. Here's some voids for express elevators. Here's the local elevators. Here's another set of exit stairs. Here's a firefighting lift, and here's another service firefighting lift, and then here's some mechanical rooms. This I just wanted to show this because it's a typology that probably never went anywhere, but I call it it's a circular core with saddlebags. This was a Xiamen Post and Telecom building, a building that a little bit like the Spire in Chicago. They built the foundations, but they never built they never built the tower, which would have been a little over 300 meters tall. But again, the core is very dense. There was the interesting thing about this building, it had a kind of an atrium that spiraled up the building. Sorry, it wasn't built. And then Las Vegas Tower, which is another one I think that Bill and I worked on, which actually the core, well, a couple things, because the core itself, the structural core is actually this whole structure. And we had talked about, actually, we had investigated using something that is now being much more fully developed, speed core, using a steel plate with a void in the middle, not because of the speed of construction, but because the soils were so bad. We wanted to save as much weight as we could on the tower. But here you can see that the architectural core is really vestigial. It's only the elevators, and there had been a few service rooms in here, but it really is kind of independent, if you will, of the structural core, even though it is a center core building. And then I was very impressed. My friends at Magnuson Klemensic have done Salesforce Tower, and this is a tower that is a very variation on a theme, in the sense that the core is actually doing all the work. That you notice there are no outrigger, there are no mega columns out here. There are no outrigger trusses. The core actually has, using a performance-based design, actually provides all of the lateral stiffness as well as, of course, the gravity load in the middle on this project. And then last but not least, this is a project that is under construction, but probably on hold for who knows how long, in Grozny, in Chechnya. It's maybe the last of the all steel supertalls. It's a tube structure, basically a special tube structure, where there's not a structural core per se. So the architectural core just needed to work within the grid of the columns. And so then you can have these funny leftover spaces sometime, but it obviously gives a lot more freedom to the architecture. So let's talk about Jeddah. I think, okay, I'm gonna try to do this in about 15 minutes. In honor of Les Robertson, I put this slide in because there were four of our teams were finalists, and Les I guess was with the KPF team. You can see him looking over Adrian's shoulder here. Wonderful guy. Just a wonderful human being, as well as a great engineer. Here's Bill. Here's Bill. Here I am. And so the SOM team, the AS+GG team, eventually we thought we would be told that the winner was going to be told on this day, which was, I think, July 14th, 2009. Well, it ended up that we ended up competing with SOM Chicago, as I like to say. We've met the enemy and they are us. And it was a very about a 10-month competition after this point, and then I guess we were lucky enough, AS+GG was lucky enough to win the competition. And so this is our consultant team. Now, when talking about cores, I'll try to focus on the core discussion when we talk about Jeddah Tower, because there is a lot to talk about on Jeddah Tower. But we had a lot of consultants on this. And the consultants that are in bold and white are the ones that had something to do with the core. Even the geotechnical team had a lot to do with the core, because they had to support it in the ground. And there was quite a bit of negotiation and stuff going on, and negotiation between all of us. So these are kind of I'll call them the major consultants, but then the other others of the consultant team, including obviously wind engineering, material handling, fire life safety, lighting, even graphics and signage, cathodic protection, which again has to do with the foundations and hardware. So of this group of consultants, the majority of them had something to do with the core, which meant I had to deal with them when we were designing the core, because everybody, everybody needs to get in there, and everybody needs to be as efficient as possible, and everybody needs to work together. So this is the floor plan, typical floor plan of Jeddah Tower. You can see it has 3 wings. It has a buttress core or a bearing wall. I don't know, Bob Sin is going to talk about the structural typology and the challenges of designing and constructing Jeddah Tower. So I won't take any of his thunder. The challenges are kind of what we talked about before: mixed use program accommodation, vertical transportation, structure and wind engineering, especially since this building is all about structure. So we're going to talk about some of the specific things in the core: stack effect, a little bit of fire life safety, building services, systems and coordination, and then everything has to do with constructability and logistics. So mixed use program accommodation, 290,000 square meters. I like to say it's the world's smallest, world's tallest building, because it's about half the square footage of Willis Tower, formerly called Sears Tower. But it's 2.5 times the height. And so this is the program: mixed use program, residential, service departments, hotel, office, retail and amenity, and observatory. The stacking, this is the stacking of the building. At the bottom is lobbies and drop-offs. I think Adrian showed some of these images before. The thing I wanted to talk about with respect to the core at the ground level, at the podium level, is it's important. I talked about the dance of the elevators. The location of the elevators is very important, because they want to be very closely coordinated with the lobbies. You want to make it very easy to negotiate your way in and out of these buildings. And so the hotel, there's three main lobbies. There's actually a 4th lobby for the observatory, which is actually on another floor, which is below this. So we tuck that away. So the hotel lobby is on the left here, and the shuttles that take you up to the hotel uses are in this zone. The residential lobby, and so actually there's hotel shuttles, and then there's service department shuttles, because the service department's use relates to the hotel. The residential lobby is on the right here, and there's 2 groups of high-speed shuttles that take you up to sky lobbies on, I think, the 44th, 45th floor and 86th, 87th floor. I haven't done this presentation in a while, so I'm forgetting now. And then the office lobby has their own dedicated locals, which you notice are actually outside the core, outside the triangular core, if you will. And so the stacking go up real quick. So the office is in this zone, so you can see the office elevators outside here. These shuttle elevators continue past the hotel guest rooms, so they can see now we start to uncover the hotel locals, which we've actually have actually started to serve these floors. And then the service departments, so you can see, so the hotel locals were in this location, service department locals were in this location, or shuttles were in this location. The residences, now there's actually 4 tiers of residences, as I mentioned. So the typical zone 1 residential floor, typical zone 2 residential floor, typical zone 3 is as the building tapers up. So you can start to see the elevators, the local elevators, and the sky lobby floors, which are at the base of each tier of residential. Is here, okay, and then between the top of the residential, we have a flex space which allows for the insertion of future floors should the marketing go well. It's something, you know, that was kind of a lesson learned on Burj Khalifa. Because you remember Bill mentioned that we actually changed use of the whole upper residential tier. From very high, I think, what did we call them? I think we called them penthouses in the sky or palaces in the sky, to what we then termed these boutique offices, which were the kind of very special hotel offices. So we have the possibility, we have soft spots, and we have the possibility of doing that. And then of course there's refuge floors every 20 floors. That's the Saudi code. There's lifeboat elevators, which I'll show in a little more detail coming up. So this is a refuge floor, typical refuge floor, and it's important for many reasons. It's actually very tiring to walk down a super tall building. So it gives the occupants a chance to get out into a place of safety. We also, the Saudis actually, this is an interesting idea, they actually have a civil defense station at each of these refuge floors, which is kind of interesting. And then we have a lobby for what we call lifeboat elevators. And I'll show you the diagram in a minute. But this lobby connects to special stops for the high-speed shuttle elevators. So in theory, you can be directed either to go back into the stair or to take an elevator back down the building for a quicker means of escape. So located in between some of the tranches or some of the zones are the technical floors at about every 30 to 40 levels. We don't have outrigger trusses in this building. That was one of the lessons learned. We avoided outrigger trusses in this, so these are just actually double or triple height floors, and so they're located in these locations. And then the technical floor is part of the core story, because everything that comes in or everything that goes up the core comes in and comes out of a technical floor. And I should preface that every service, electrical, plumbing, drainage, air systems, all come out. So what I'll try to see if I can zoom in on this. If you can see, this is just the ductwork, let alone the electrical equipment or the plumbing equipment. So there's a myriad of stuff that has to come out of risers in the core, go in to feed these machines, and then again go back up the building. So it's hand in hand with the core is this serviceability. So then we finally come to the observatory levels with the Sky Terrace. Adrian told the story about the helicopter pad that became a Sky Terrace. So so now you can see the actual massing of the building starts to impinge on that triangular structural core. And then of course we have a spire, and I'll let my friend Bob talk about the spire. So vertical transportation, I'm gonna go through this very quickly. We have in the case of Kingdom Tower, we actually have 57 elevators with 64 cabs to service the building, but they're in a core that has 18 spots for these 57 elevators. So as Bill pointed out last time, the way that we do that is we incorporate shuttle elevators to stop at sky lobbies, and then we incorporate local elevators taking over the space of other elevators that have dropped out, of other locals that have dropped out. So the way we do this is in the zone between the elevator machine room and the pit. The elevator machine room at the top of the one set of locals. We then have the pit and the rest, and the shaft containing the next set of locals stacked on top. So we do that several times. So here's just a very brief looking at the high-speed shuttles. Our travel distance, our highest elevator technology now allows us to go over the 500 meters that we're limited at when we did Burj Khalifa. So we're at 640 plus meters. The technology that allows us to do that, as you may not know, the elevator cab is not the only thing that the elevator machine is lifting. There's actually, in the case of the shuttle elevators going over 600 meters, there's 3/8 of a mile of steel cable, and so the technology, you can only make your machines as big as you can. You can make bigger machines, but what's actually the technology that's being employed in Jeddah Tower is a technology called it's a super rope. It's ultra rope, and the cable is now not steel anymore, but it's actually a polyamide with some reinforcing. So it's basically more or less carbon fiber. So it reduces the weight by about 1/8 of the weight of steel cables. Another issue that we have to deal with is windage. That is to say, the pistoning effect or the speed of the high-speed elevator cab. The cab, as it goes high speed, you can either do one of two things. You can either make and I'm skipping around here a bit. You can either make a larger shaft, which there it is. You can either make a larger shaft to allow for the car and the counterweight to not block the air, or you can add shrouding. That is to say, you can use aerodynamics to the top of the cab and the bottom of the cab to ease that, because it will help it cut through the air. And you add shaft clanging. You try to make the shaft as smooth as possible. You try to introduce active roller guides, or this is poor man's animation. You introduce cross shafts that allow the air to the hoist rate pressure to relieve itself. You've seen this picture before, I'm sure. Building sway and resonance has a lot to do with the vortex shedding, as Bill explained, the movement of the building, the capacity, but it also has to do with the elevators. And it's a very important thing, because these elevator cables, the elevator is like a pendulum. And there are two sets of cables. There's a cable that hoists the elevator, and then there's a trailing cable that's below it. And so we actually do studies. We start with the wind engineering. We get the behavior from our friends at RWDI of the building under wind. And then we do an analysis with the help of Kone in the case of Kingdom Tower or Jeddah Tower, Otis in the case of Burj Khalifa, to find out if there's a resonant frequency. Because what happens is, if there's a resonant frequency on the cable length, that cable will start slapping around the shaft and could do damage, and it could also disable the elevator. Stack effect, very, very briefly, everything in the core is vertically connected, and in places like Dubai, the stack effect is actually reverse. It's cold air trying to rush out the bottom of the building, whereas at Sears Tower or Willis Tower, the warm air is trying to rush out the top of the building. So what do? With respect to the core, we try to construct the shafts as well as we can, as airtight as we can. We try to protect the shafts, which would keep them generally within the core, and it's not only mechanical shafts, but it's the elevator shafts, it's the stair shafts. So we try to introduce a second set of doors, if you can see where my cursor is, to separate the core from the exterior wall, because that's where the air wants to go. And then we interrupt and we offset a continuous shaft. So for instance, at the areas of refuge floors, we'll take the stairs out. And I think I've got a slide coming up. Yeah. So we at the areas of refuge floors, we'll transfer the stairs. So they're discontinuous. So they're not 162 stories of stairs, that there may be 30 or 40 floors, or 20 floors in the case of Jeddah Tower, so that we can interrupt that. And then this is actually the lifeboat elevators, and I am cognizant of the time, so I'm going to go very quickly. This area of refuge floor, again, a lobby for lifeboat elevators. In this case, these were the residential group 3 and 4 shuttles that open up onto the floor. And the purpose of these, I think I mentioned, so this is diagrammatically the shuttles that we've used. So they're all the high-speed shuttles. They're all in protected enclosures. They're inside the core, so they're very good locations. And they are actually separate from the firefighting elevators. They're not, so they wouldn't be used. The firefighting elevators are used exclusively by the firefighters. So let's finishing up here. We're going to talk about building services, because unfortunately, you know, and there's I told Carol there should be another series at least with a MEP engineer, because the coordination is in the core of these systems is of critical importance. And we talked about the environment changing with height, air density, solar radiation, temperature, moisture, aerosols, and wind. So you're really dealing with a different climate at the top of the building than you are at the bottom. So it's like being in Sacramento at the observatory, whereas you're still back in Jeddah at the base of the building. So there's a lot of things that happen. That's a very interesting story. The other thing, the obvious things about height is you have to deal with hydraulic pressure. If you had a column of water at the height of Jeddah Tower, you'd have 1,420 psi at the bottom. You can't deal with that. So what do? We split the systems. And so again, these mechanical floors that happen every 30 or 40 floors are very important, because we create secondary pressure zones. And last but not least, talking about building services and system coordination, in order to make these buildings viable, you have to optimize everything. And I know Bob will talk about it with respect to Jeddah Tower, how every bit of concrete has to work not only laterally, but in gravity. And every mechanical system, electrical, plumbing, fire protection, fire alarm system, communication, security, vertical transportation, all the architecture, all the structure has to be optimized. And the only way you optimize that is you do massive amount of coordination. And this is where I have to give a plug to the teams, because coordination doesn't happen although some people like to think of it, coordination doesn't happen with the press of a button. Even though we have wonderful tools, and we'll talk about the tools in a second, there are still 19,000 plus openings just in the structure alone. And I think altogether, there was over 100,000 openings that had to be individually coordinated and located. And the openings can only be located if you can locate the duct or the pipe that goes through the openings. So how do we do that? So the team, the biggest impediment and of course the biggest tool can be the team. And when we start a job, we're trying to figure out what the building wants to be, because the building will kind of tell us what it has to be. You know, structure, you can't push around the structure too much. You can't also push around the elevators too much. So we start with a lot of constraints. And the only way that we can do this, is we found, is you really have a very detailed coordination schedule. And just the general principle is these buildings are generally fast tracks. So we're in the ground doing the foundations. Foundations might take a year to build. So during that year, while we're designing the rest of the building, we are starting at the bottom of the building and coordinating our way up to the top. This is a tool that we used on many of our projects, coordination schedule. And of course, these days we can do building information modeling. And this happens to be the podium. This happens to be those technical floors I was showing you, so you can see how much stuff is on the floor and everything. As I said, every pipe generally and every duct has to go into that core and go up and down the building. So at the end, after you spend literally maybe 14 months, 16 months coordinating the building, we're like a well-oiled team if we're still talking to each other. This I'd like to give kudos and apologies to Thornton Tomasetti and ESD and Jensen Hughes and others. This is the architectural team for AS+GG that did Jeddah Tower. This is the team that finished it. And then I put the slide in for Bill because he's photoshopped in here. This is the SOM Burj Khalifa team. Now this is the multidisciplinary team. So if it takes a village to raise a child, it takes a village of disciplines to build one of these buildings. And without the team, it doesn't get done. So that's it.
Thank you so much. Actually, it is 7 o'clock. So I think we're not going to take chat questions from the audience in general. I think you all know where you can find Peter if necessary. And it's going to take 2 or 3 viewings, I think. And people will certainly be able by Thursday to be able to watch the edited video on our website, just as you can see all of the previous lectures on our website, or through our YouTube channel, where I think this live stream will still exist until the edited version appears. So we will be able to watch over and over again the complexity of the core that you design, that you characterized for us so well. And since I started the discussion saying that I wanted to make a big dumb observation by someone who is a layman rather than an architect or an engineer, I think you've clearly shown that my big dumb observation about the primacy of the core, the center core built of concrete, is not at all a dumb feature of the building. It's an extraordinarily complex design problem. And so thank you for that. I mean, it's just extraordinary how much thought and precision and coordination needs to go into the core design. I guess maybe just by way of stealing a few more minutes to ask some big questions that may have occurred to other people, or are the kind of thing that I hear generally with reservations about super tall buildings. And we will talk about, I know with Bob Sin next week, the why go tall and what are the limits to going tall. Spoiler alert, physiology of the human being is one of those constraints. But certainly life safety, which is one of your specialties, is a concern that you've demonstrated so well in the features, sometimes the code features in countries other than the US. So can you tell us a little bit more in the comparative framework between the New York or the Chicago model and what you find in other countries around the world? And do you assure us that we're safe no matter where in a global super?
Yeah, I think people take these buildings very seriously, and not only the designers, but also the local authorities. So the resultant that you see in Jeddah Tower was based on many meetings with the local authorities and much negotiation. And so but you always start these buildings. You predicate the design. Building to code is building to the minimum standard. You always go in on any of these buildings and you think about enhancements. Now you have to be careful, because sometimes the road to hell is paved with good intentions. So you have to be careful that you don't you're not obviating something that's more important than something that you do or creating. You also don't want to create so many complicated systems. Because face it, a lot of these buildings are in parts of the world. We're seeing it more and more now in parts of the world that, you know, maybe the maintenance of that you know, that very complicated active system is not going to be done as well. So you always think of fire life safety in terms of active and passive systems. So passive meaning things like the structure of the core. I mean, the very fact that the stairs are now located within a reinforced concrete wall that at the base of Jeddah Tower is 1.2 meters thick. So that's pretty robust. But in the typology, I think if you compare Jinmao to Burj Khalifa to Jeddah Tower, we've seen a progression. On Jinmao was the first time I was introduced to the idea of areas of refuge, and we were directed by the Chinese authorities to include them, but it was very early on, so there's only, I want to say there's one in the office zone, in the middle of the office zone, about at level 25. So because office goes about to level 50, and then there's when we moved everything out of the core, the areas of refuge became just basically glorified wheelchair spaces on every other floor. So there was no code. There was just like, this is the idea. On Burj Khalifa, we took that idea and we introduced them because there wasn't a code in Dubai, and we kind of designed to the IBC International Building Code. But remember, we designed the building in 2003, 2004. So the layer that we introduced was the lifeboat elevators. So we introduced, and it came actually a little late in the process because we weren't able to directly connect them to the areas of refuge. So the areas of refuge are actually one level below the sky lobbies, which then you connect from the area of refuge to the sky lobby to catch a shuttle to go down again. And the way you do that is we have active signs. There's signage, LEDs in each area of refuge. They'll say either continue down the stairs or go up a level and take the elevator. Now, where we are with Jeddah Tower, Saudi Arabia, as part of their code, mandates an area of refuge floor every 20 floors, which is, and it's not just a partial floor; it's a whole floor. And because this was the world's tallest building, going to be the world's tallest building, we had a lot of negotiations with civil defense. At one point, they wanted us to not have windows, to have the concrete walls around the side, around where the windows are. They at another point they introduced this idea, which I think is actually a great idea, of having a civil defense person on the floor to manage the floor. Because think about it, if you have 20 floors of people coming down, sitting in this one huge space, they need to be managed. And so in the core of on the area of refuge floors, there's a civil defense office which has a public address system that and monitors that can monitor the floor and give announcements to the people saying it's okay, you know, or continue down the stairs or whatever. And there'll be like a civil defense officer there. They're also we also are using them as I'll call them way stations. There's a breathing apparatus, you know, that firemen use these days. So they can fill their tanks in those civil defense offices. And of course, it's all tied into the stuff. So I mean, there has been quite a bit of development. And of course, last but not least, the lifeboat elevators open on those floors, and so they can be used for means of escape, which basically reduces the amount of time for the last person to get out by more than half.
So maybe one last question with a quick answer, although a difficult one. So you've talked about the innovations that, whether through codes or in fact creating a code in order to deal with this innovative new type of building. Since the core seems to be one of the givens in the typology of design, and we have heard about the inventions and improvements within concrete and composites, so that one doesn't even call it concrete anymore. It's a new kind of material. Are there things that you can see within the core which seems from one hand so unconsidered, but from the other end of the spectrum so fundamentally important to this core value? Are there places for innovation that could completely re-envision the core, reinvent the core?
That's kind of difficult. I think maybe more on the building services side. I mean, there's been a lot of talk about wireless connectivity. People are kind of a little bit leery of it for things like a fire alarm system or such. But a lot of what we do, I think there's the technology. The obvious one is the introduction of maglev elevators, which I'm not sure where ThyssenKrupp, as you know, I'm sure you know, has been developing the ropeless elevator. I'm not sure where they are right now with that, but with the introduction, once we're freed from the vertical shaft for the elevator, I mean, we could be doing a lot of things. I mean, you could distribute those, or you could bring occupants up to one point and then take them sideways and then take them up the outside of the building, or you could distribute that. So that may be the most disruptive, potentially disruptive technology right now.
Well, I guess this is a good way of saying to wait until next week, where we can tune in to Bob Sin, who's going to reinsert gravity into the discussion of the Supertall with the pure bearing wall of Jeddah Tower, and explain to us those kind of fundamentals. But we thank you so much, Peter, for the kind of ultimate tutorial on why the core matters and all of the things that we need to think about when indeed this most central part of the design of the Supertall begins to take shape.
Yeah, my middle daughter would say the core is the forgotten child of the family, and so we can't forget about the forgotten child.
Absolutely not. Core importance.
Yes.
Okay, so thank you, Peter, and thank you everybody for joining us tonight, and come back next week in order to talk about ultra tall, how do we build now, with Robert Sin from Thornton Tomasetti. So good night, everybody. See you next time. Okay, 6 o'clock. We've got everybody in. Hi, welcome everybody. I'm Carol Willis, the director of the Skyscraper Museum, and welcome to the 8th of the lectures in our series, Worldview, Designing Global Supertalls. We have tonight an architect who's entering our phase 2 of the lecture series, which focuses on engineering, with Peter Weismantle, who is the now consulting director, formerly director of Supertall building technology at Adrian Smith and Gordon Gill Architects. And tonight he's got an extravaganza of building cores, and is an absolute connoisseur of cores, and we are going to become something of the same. Last week, if you joined us with Bill Baker, you know that we talked about different approaches to structural engineering. Let me show you the overview of the lecture series first, as I do the introduction, having already mentioned the title of the series, and you have been, I hope, with us on previous lectures when the architects talked about the lineup that you see here below you. The the phase of that we're in now with the engineering, the 21st century Supertall, launched last week with Bill Baker, who will be mentioned a number of times in the course of this evening. And I did want to also mention that we're dedicating this second half of the series in particular to our friend and colleague who passed away last month, Leslie E. Robertson, a great structural engineer who inspired many of those younger engineers who are speaking about building tall in this series. So we'll be thinking of Les as we look at the various innovations across the series. But as I said tonight, we're looking in particular at the core. And this is an issue that I recruited Peter Weismantle to talk about, since he looks at all aspects of building technologies in the Supertall, which are very often very confounding problems and need to be designed, as Bill Baker mentioned last week, kind of like a Swiss watch. There are so many things of MEP engineering, of vertical transportation, of life safety that need to be fit into a compact core. But all of that kind of information that makes one a connoisseur of cores and a real expert is not the way that I began to realize the importance of the core, and what in the title that we gave this today's talk, core value, which exists in the 21st century Supertall. What you see here is one of the earliest Chinese Supertalls. It's the core of Jinmao, just beginning to rise in probably about 1996 or 97. And I wanted to mention that Mark Sarkeesian from SOM, who worked on Jinmao, as did Peter Weismantle when he was at SOM for his 31 years before moving on to Adrian Smith and Gordon Gill Architects. This is a building which so clearly shows us the tradition of concrete construction, which will typify the 21st century Supertall, and especially in the Chinese examples that I'll show you, but also in the buttressed core approach that Bill Baker talked about with the Burj Khalifa last week, and that Peter will talk about in the core that he designed for Jeddah Tower. And next week, we'll hear Bob Sin, the structural engineer for Jeddah Tower, talk about all aspects of that design. But here was the big, dumb idea that finally dawned on me in my researches about the Supertall, as we collected not just renderings of the buildings that were going to rise with their gleaming glass facades, but also the construction views underway with these massive projects. So here is in Hong Kong, the ICC. You see the massive concrete core and the narrow lease span for the office floors that surround it. You see the core rising above the diagrid exterior tube at IFC in Guangzhou. You see what Carl Fender talked about 3 weeks ago, I guess, the rising mast of the core of the Merdeka Tower in Kuala Lumpur, which will go to over 600 meters. And one of Peter's cores that you see here under construction, the Chengdu Greenland Tower, that Dennis Poon, as the lead structural engineer for Thornton Tomasetti, will talk about in a few weeks. And here's the Jeddah Tower with the buttressed core strategy for construction, the pure bearing wall of concrete, but the core that rises ahead of the rest of the formwork. So this kind of fundamental value of the core is what Bill Baker has called in discussions, at least that I've had with him, the freebie for the structural engineer. But to distinguish the architectural core, as Peter will illuminate in his talk, where so many of the operations of the building need to be worked out in the plan level as well as in the elevation. So in this drawing that you see on the left of the almost like kind of Tiffany setting of the central core of the Jeddah Tower, you see the connoisseurship of core that needs to be designed into the project, obviously for the very beginning, because that core value is also a core principle of both the structural and the architectural design. So I'm going to invite Peter to turn on his camera so that you can see him. And then I think he thinks he will disappear as he begins to share his slides and go widescreen. So I'm now going to turn off my video and hand it over to Peter Weismantle, who again, I will say is an architect and not an engineer, but who has specialized in these building technology issues, first at SOM and now at Adrian Smith, and has been involved in pretty much every Supertall project that you can count from those two firms, and has led the design team on these core issues of design. So Peter, please take it away.